As we mentioned in the last installment, we know that the universe is about 14 billion years old and that it began in a singularity and the Big Bang, and it's been expanding ever since. So how do we know this? And there's lots of lines of evidence for this. But one aspect of it, particularly about what happened in the first few minutes, of the universe, comes down to some work at a very famous place, and you may recognize this as CERN. And this is located in Switzerland. It's a huge particle collider known as the Large Hadron Collider, also known as the LHC. And what it is a particle accelerator in a loop, and this loop is 27 kilometers, or about 18 miles around, like so. And you can see there is a smaller ring for a smaller particle accelerator there at CERN. And the European Union is planning to build a larger particle collider that has a circumference of 100 kilometers, much, much larger than the LHC. And so that's what this forms a component of how we know what we know. Well, what's inside this path is a tube, and if a person were standing inside this tube, they would be about this tall, to give you a sense of scale. And inside this tube, we accelerate particles at very, very high speeds, and we collide them into each other. And when they collide, when these particles come together and collide in the location where they do collide, those particles smash apart, and you can see all different kinds of particles form. And we affectionately refer to those particles, that whole list and names, the whole listing of all those particles, as the particle zoo. Turns out when we take particles like protons and neutrons and alpha particles and we send them into each other at super high speeds, they collide, smash apart, and form things that are much smaller than protons and neutrons and alpha particles. And we study the behavior of those things in electric and magnetic fields. And of course, these are happening at super high speeds and they're super small, so we need to have a camera or a detector. And this is a cross-section of the camera or the detector. So the particles are coming in like so, they collide, and this detector is together, and all of this around the outside is the detector. Now, this is known as the world's largest machine. If you look carefully, you might notice that there's a person standing down here inside that frame, and these are cranes and forklifts and things, and this whole dimension here is about 5 stories tall. And so one way to think about this collector, the particles come out and they take all of these trajectories outward after the collision, and all of these are detectors, or you can think of them as being like a camera. Now, of course, if you want to take a picture of things that are traveling very, very fast, you need a big camera. So there's a lot of sensors here to detect the particles going off at high speeds. So the result of all of this is, and discovering the way these things have evolved, is the forces that are involved. And so what we've come to see is that as we get higher and higher energy in the collider, as we make them, as they go faster and faster and faster, that's higher energies. And those higher energies replicate the conditions like the Big Bang. So if you have higher and higher energies, you can smash smaller and smaller particles apart. So ironically, to study things that are smaller and smaller and smaller, you need higher speeds, higher energies to look for smaller and smaller things that existed shortly after the Big Bang. And so what we've been able to tease out from all of this is that if the Big Bang occurred here, the forces didn't all appear at the same time. It's not like the universe was created and all the forces existed. And so the first of the forces that appeared after the Big Bang was the force of gravity, which you see here depicted. And the next one to appear was the strong force. And the next one to appear, or the final two to appear, were the electromagnetic and the the weak force. So what this means is if you go back, here is now in time, here is very shortly after the Big Bang, 10 to the minus 42 seconds. After 10 to the minus 42 seconds, gravity splits off, and after 10 to the minus 34 seconds, the strong force splits off. And the strong force is what allows quarks to stick together. Now, at this point, you might not even know what a quark is yet, but it turns out quarks come together and they form neutrons and protons. So it's the strong force that allows neutrons and protons to form ultimately, and therefore after that, atoms. And so after the Big Bang, we have gravity forming. We have this force that allows quarks to come together and form nuclei. And then after the nuclei of atoms form, the electromagnetic force forms, which allows electrons and protons to be attracted to each other and protons to repel each other. And the weak force comes into play, which allows for the existence of neutrons. And since we've gotten to modern times, we've studied the evolution of the universe, it appears that there may be another force called dark energy. And dark energy is something that causes galaxies to repel each other. Now, we don't know what dark energy is. It might be a force. It might be energy. It may be an artifact of space-time itself. It may be an artifact of time. But in any case, it may be a fifth force. So in the universe, as we get to now, there are really, truly only four fundamental forces: the strong force, the electromagnetic force, the weak force, and gravity. So everything else we think of, all forces we think of, except the four fundamental interactions, these four interactions, we call them interactions, are derived forces. So there's these four derived forces: gravity, electromagnetic, strong, weak, and dark energy. The strong force and the weak force operate on scales much smaller than the size of an atom. They operate inside the nucleus. And dark energy, whether or not it's a force, operates on scales larger than a galaxy. So what that means, and this is incredibly important, is that everything we deal with in this course and everything we deal with in our daily lives are a combination of gravity and electromagnetic force. That's it. Everything else is derived from these two things. All other things we call forces are derived from gravity and the electromagnetic force.